Hello, good afternoon. Today we're going to work on lesson 4.6. And in lesson 4.5, we talked about measures of center and where is kind of like the center of our data. We talked about the mean, the median, the mode, in a couple different avenues of looking at that. And now we're going to talk about how does our data vary from each other. So it says your results may vary. So the quote says, research shows that there's only half as much variation in student achievement between schools as there is among classrooms in the same school. If you want your child to get the best education possible, it is actually more important to get him assigned to a great teacher than to a great school. So if you want your, so what we're going to do is we're going to learn about measures of variation today. Measures of variation. So the first measure of variation that we're going to look at is the range of data set that is between the largest and the smallest values in the set. So the range. You're going to have to know how to calculate this for the project and for the final exam. So it says the first list below is the weights of the dogs in the first picture, and the second is the weights of the dogs in the second picture. So we have here the weights of the first set of dogs. There's a little itty bitty dog there. And then we have some more dogs here, really big dog there. Find the mean and range for the list. So we're going to do the mean under here and then the range. So we should get out our Desmos. So we have our data here in Desmos, and our first picture, we're going to say the mean of X1, oops, X1, the mean of Y1. So the first set of dogs has a mean of 65.25, and the other dogs has an average of 64. Okay. Which is interesting because you would think that the second picture would maybe have an average of bigger dogs just because the one dog in the middle is pretty big. And then we're going to go back and look at the range of both. So the range of the first set is from the largest, so 73 to 58, which is 15. And the range here is from 125, which is the biggest, to the smallest dog, which is 30, which is 95. So there's a big range in this because that one really big heavy dog and then the little dog. Describe what you notice about the range and mean for each group of dogs. So their average, the average weights are similar. But the ranges are much different. And you can see what we just described on the difference of these dogs are all similar to each other in size, where these dogs are, vary greatly from each other. So number 3 says, why is the range somewhat limited as a measure of variation for a data set? And that's because you are only looking at the smallest and largest values. So it's kind of like when we looked at the mid-range, back in lesson 4.5, we only looked at the smallest and the largest as well, and that was a limitation then too. So we are going to introduce standard deviation. It says the range is a limited measure of variation because it ignores all the data except the highest and lowest values. If most of the values are similar, but there's just one unusually high value, the range will make it look like there's a lot more variation than there actually is. For this reason, we will next study standard deviation, which is much more reliable and commonly used measure of variation. Standard deviation is a little tricky to compute. Eventually, we'll learn how to use technology. We're going to really only use technology. But here is important. This is a bit of an oversimplification, but it's still very useful in understanding what standard deviation is designed to measure. So right here is important. Standard deviation essentially describes the average distance that each data value is from the mean. It says, read the description of standard deviation in italics above carefully again. Why does standard deviation provide a very reasonable way of describing how spread out a data set is? Standard deviation essentially describes the average distance that each data value is away from the mean, because it's finding all of those deviations above or below the mean and then averaging all those out. How to put that in words. Standard deviation comes in two delightful flavors, population and sample. We talked about that with our mean as well. As we saw in lesson 4.4, in many cases, data are based not on every single member of a population, but rather a representative sample. When the standard deviation is computed for a data set derived from an entire population under study, it's called the population standard deviation. When it's based on data derived from a representative sample of a larger population, it's called sample standard deviation. Computing standard deviation by hand is pretty complicated, and the truth is that we'll eventually rely on technology to do the computation. In fact, your instructor might have you do that right out of the gate, and that's fine. But we feel like learning and using the formula is useful in that it will help you understand what exactly standard deviation is measuring. So we're going to start there and learn how to use technology later in the lesson. In statistics, it's far more common to work with a sample than with an entire population. So we will develop a procedure for computing sample standard deviation. As we illustrate this procedure, try to pay attention to the key ideas described in the solved example. After that, we'll ask you to think about what those key ideas really tell us. So I am going to show you this. Okay, the solved example. So we had the 8 dogs in the from the picture where the second picture where there's a really large dog and a really small dog. It says find the mean. In this case, we've already done that. It's 64 pounds. Key idea, at its core, standard deviation is a comparison to the mean, so it makes perfect sense to start there. Then we're going to go and find the deviation from each individual data point to the mean. So we're going to take the data point and subtract the mean. So 30 minus 64, 85 minus 64. Notice the data values that are below the mean. 30 is smaller than the mean. Then the deviation is negative because it's under the mean. 85 is a data point that is above the mean, so its deviation is positive. Okay, so the key idea is we want standard deviation to be a measure of how far the data values are from the mean, so we should subtract to get the distance from the mean for each value, which we did here. Square the differences. We'll just add another column to compute to our table here. So we're going to take these differences and square them. And so the reason we have to square them is that if we were to just add them, some are positive and some are negative, it could by chance happen that they add to 0, which would show that there's no deviation at all. And so by squaring them, even though it compounds the value, it at least makes all the values positive. Okay, so our key idea here is if we just find an average of all the distances from the mean, we'll always get 0, which isn't particularly enlightening. Try it. By squaring, we eliminate the signs to avoid the issue. Okay, so add up the squares of the distances. This is just plain old addition, and we'll see why in a second. So we add those distances, and then we're going to find the average but we're dividing by n minus 1 instead of just our sample size, okay? So if we were had a population, we would divide just by n, but because we have a sample and we've done some estimating with our mean, because it's just from a sample, it's not from the population, we're going to account for that estimation in the mean by subtracting 1 from our n, from our sample size, okay? So it says to get the actual mean of the squared distances, we would divide by the number of values here. But when you have a sample of data values from a larger population, it's almost certain that there's less variation in the sample than in the overall population. So to account for that, we divide by n minus 1 rather than n, making the result a bit larger. So then we're going to take the square root of that averaged value. After this step, we have our standard deviation. The sample standard deviation for the dogs in this picture is 30.7 pounds. The key idea is, remember when we squared all the distances to get rid of the signs? This is where we're basically undoing that square. So we squared all of them and they seemed really large and inflated. Remember when we got those down here, all these really large numbers by squaring them? So now that we've got the average, we're going to square root it. So we're going back to our unit of measure of pounds. So now let's see how you did in understanding the key ideas in the solved example. We set out to develop a measure of how far on average the data values in a sample are from the mean. Based on the key ideas, explain how we are able to accomplish that. By averaging the absolute differences from the mean. And when I say absolute, I mean not taking into account whether it's positive, negative, just looking at the absolute difference. Okay, use the procedure from the solved example to find the standard deviation for the weights of the 4 dogs in the first picture at the beginning. So we're going to find the standard deviation. So we're going to use Desmos, okay? So we're going to go to Desmos. And we're not going to do this by hand. So our 4 dogs are in X1. So we are going to say STDEV, and then in parentheses, X1. Okay. And we can verify this is right, because if we do the one from the large list that we did in the example, the solved example, we can say STDEV of Y1, and we would get the 30.7. Okay, so for number 6, our standard deviation of the list of 4 dogs is 7.37. So and because this is a sample, we're going to use a little s for sample standard deviation. Sample standard deviation is a little s. And so for us, it's 3.37. Number 7 says, carefully describe exactly what the standard deviations from the solved example in question 6 tell us about the dogs in the pictures. Include a comparison of the 2 standard deviations. So on average, the dogs in picture 1 vary from the mean by 7.37 pounds, whereas the dogs in picture 2 vary from the mean by 30.7 pounds. So what that tells us is that the dogs in picture 2 have much more variation. Picture 2, dogs have much more variation. So here are the formulas. If you have sample data, you're going to use this formula. And if you have population, you're going to use this formula. Now, we're not doing anything by hand, so don't worry about that. So in Desmos, for sample standard deviation, you're going to say STDEV of your X1 or whatever, wherever your data is. And if you have population data, you're going to do STDEVP. STDEVP. Okay. So that's what you're going to use in Desmos. So let's go to page 476. It says a word annotation. We use a lowercase s to represent the standard deviation for a data set. The symbol SX is simply what's used on the calculator screen. Simply, we use the lowercase Greek sigma to represent population standard deviation, not this sigma. So notice that we don't have to worry about that because we're using Desmos. So when you talk about sample standard deviation, you're going to show me a little s. When you talk about population standard deviation, you're going to use this. It looks like an O with a little tail at the top. It's called sigma. So the table below shows the number of arrests in the U.S. for possession of marijuana in thousands for the years from 2008 to 2017. All data were gathered from the annual Uniform Crime Report published by the Federal Bureau of Investigation. Find the mean and sample standard deviation for the number of arrests and include units. Why is it appropriate to find sample standard deviation rather than population? So let's go to Desmos. And this is going to be okay. And now we're going to do another table. Notes. We're going to do arrests. Let's just make this a note here. I'll put it in the table. And we're going to type these in. And they asked us to find, oops, the mean and sample standard deviation. So the mean of X1 and the sample standard deviation. Notice I don't have a P because it's sample standard deviation. So the mean is X bar is 578.4 in thousands. So it's really 578 and 4,400 arrests. And then the sample standard deviation is 50.51 or 509, we'll say 50.509, which is 50,509 arrests. And I will show you my paper here. Again, notice here in Desmos, we don't use a P because it's a sample standard deviation. So here's our mean. I wrote it out in thousands. And here's our standard deviation. Why was it appropriate to find the sample standard deviation rather than the population? And that's because we don't have arrests for every year. It just says for these particular years. Standard deviation is easiest to interpret when compared to the size of the mean. For example, a standard deviation of 10 in a data set with mean 20 indicates a much wider spread than a standard deviation of 10 in a data set with mean 200. To help make this easier, we can find the relative standard deviation, also known as the coefficient of variation. This number usually denoted C with a little v, and it looks small there, but it's C with a little v down here in the subscript. Is the standard deviation divided by the mean. It's literally what percent of the mean the standard deviation is. And so you want it to be very small. And the larger, a large CV means there's a high standard deviation. And so you calculate the same, whether it's for sample or population, it's taking that standard deviation and dividing by the mean. Find the coefficient of variation for the rest data above. So that would be the 509 divided by the 578,400. And that comes out to be 0.0873, so 8.73%. A standard deviation is 8.73% of the mean. We want this low. Lower, the lower, the better. Okay, we want this to be low. Do you think the standard deviation and coefficient of variation for this data set would be more likely to be used in an argument by someone who's in favor of legalizing marijuana or against? So you would want our mean to be low because our data is kind of up and down, right? Lots of arrests over the years. Who's in favor of legalizing marijuana? So there's a lot of arrests going on. So you would think that with the standard deviation being low compared to the mean, it means they're consistently arresting a lot of people. So they're saying legalize it. They would use this to support legalizing marijuana because arrests are not going down. Now, if they look at the number of arrests in the last couple of years, like here in Michigan, since now marijuana is legal, then those number of arrests should go down. And so then our variation should go up because there used to be higher arrests and now there should be lower arrests, but we don't really have that data yet. Find the coefficient of variation for the 8 dogs from the solved example in the class portion. Compare it to your answer to question 3. What can you conclude? So the 8 dogs had a mean and a standard deviation. And their standard deviation was 30.7 pounds, and the average weight of the dogs was 64 pounds. So it would be 30.716 divided by 64. Divided by 64 is 0.47.9. Whoops, 30. So 47.99%. So 0.4799. Let me write that again. 0.4799. What can you conclude? And this is an agreement. High variation. So this is exactly what we said back in question number 3, that our standard deviation is very high, and you can see that our standard deviation is almost 50% of our mean, 47.99%, so high variation. Okay, so for questions 6 through 8, identify the data set that is likely to have a larger standard deviation. Make sure you explain your reasoning, like with scientists and sentences and stuff. No calculations necessary, just think about the data. Okay. So this says data set 1 and data set 2. Data set 1, the lowest is 10, the highest is 16. They're kind of all around each other. I'm definitely thinking data set 2, and you can see because we've got low, high, high, low, middle, high, low, high. So I definitely think it's data set 2. A lot of variations of high and low. Number 7, data set 1 says a 40-yard dash times for starting running backs in the National Football League and 40-yard dash times for every student in your math class. Which would have a larger standard deviation? Well, I think we would be safe to say that we think that running backs in the National Football League and the NFL would be similar to each other, so they would not vary much from each other. Would not vary by much from each other. 40-yard dash times for every student in your math class. There could be, I mean, we're comparing males and females, and it could be fast and could be slow, so could vary quite a bit from each other. And so you're choosing data set 2. This is your lesson check for this lesson, page 477 here. Okay, question 8. Data set 1 says average monthly high temperature in Chicago, and data set 2 is the average monthly high temperature in LA. So my guess is average monthly high temperature in Chicago could really vary, right? Because summer months, it's going to be pretty high. Winter months, it's going to be pretty low. In LA, I think you could Google this and say that average monthly high temperature in LA is not going to vary too much. So definitely data set 1. Okay. Number 9 says, a professor has 2 sections of Math 115 this semester. The 8:30 a.m. class has a mean score of 74% with a standard deviation of 3.6. The 2 p.m. class also has a mean score of 74%, but a standard deviation of 19.2. What can we conclude about the students' averages in these sections? Well, because the 8:30 a.m. class has a smaller standard deviation, they all scored similar to each other. So the 8:30 a.m. class had scores similar to each other, around 74%. the afternoon class, they had an average of 74, but they must have had some really low scores and some really high scores to have a high standard deviation like that. And the last question for lesson 6 says, in the technology portion of the portfolio, you'll be analyzing the heights of every student in your class. So we are not going to be doing that. We are going to be doing other things because we have a project surrounding the topic of the measure of center and the measure of variation. So you'll be getting to take a look at that here soon. So catch me back for the very last lesson of the semester for lesson 4-7 soon. Have a great day.